Okay, so next I will do the end structure and compactification. So we have this end. Maybe I should have done this earlier, but so ideal boundary structure of end neighborhood is some pair UF with a smooth embedding of F into the product space, and so the sigma with the image is this, and so ideal binder structure is a diffeomorphism with U0 to this. And so if you have another one, then they are compatible if there's another boundary structure which uh, goes into the same. Okay. And so these will give you compression of all along E. And so these will be called by say some identification and compactification. And so isotopy is what we mean is that the ones that extends to this kind of boundary structure. Okay, and right, and then for the radial end structure, you can also give your end compactification, and these are again defined very similarly, and you always have some uh, the these will always extend. This isotopy has to extend to the boundary as well. So the following were defined uh, as of these new orbifolds and so on. Okay. So then we want to define the definition of deformation spaces. So if so these orbifold with the Rn or Tn's are isotopic, if you can find the isotopy like this, and so this radial end structure exists for each R end or Horst-Becker R end, and I send the radial foliation of neighborhood to the radial foliation of the new one, and it extends to the O bar, this compactification for the radial foliation and the totally geodesic radial boundary. Okay, so those are the isotopies we'll be working on. And so we look at the developing map associated with any convex projective structure. Then we extend to this O head. Okay, so we will only use ones which extends. Okay, so we can show that by isotopy. We can always do that later, but we will just look at the ones which extends. Uh, so this devil bar is smooth. You can assume these are smooth uh, and so on. So the way we can always right. So these are the fact that you can always have any two immersions which radial, if you go to radial, then they are actually smoothly isotopic as long as they are the same in the so in the compact path, okay, away from the end, then you can always make them isotopic, preserving the identity here. Okay, so these are because these are just trivial vibration foliations, so you can use that. So here I can always make the developing map to extend to the smooth one. So what I do is the radial and projectivization. So the way to do it is to look at these close neighborhoods and then of the same neighborhood, and then you look at some something in the right in the so some ray in U prime, okay, and containing some point here, and then the so maximal ray in U tilde prime, and So you can parameterize by sending Lx in the boundary of u prime to infinity and the other end to 0, and then x to be 1. Okay, so once you have this u and u prime, then you can define this function on u prime, and then there is a projective map from R plus to RPN by sending 0 to VE and 1 to this dev x, and then infinity to this point here, and the Px to be the vector at this BE at this parameterization. And so pi e denote the mapping the point of radial A to the equivalence class here. So then this defines this smooth map from Deban to here using this px pi x y for y in here. Okay, so uh, right, so pi x is this map, and then you send back to RPN using this map. So it is a map from the Lx to the projective space, and so then you have to argue that this is actually extend to smooth map here. Okay, so that's what I'm doing over here. Okay, and so the argument is kind of long, but you can do this. So then you call this radial and projectivization. So you choose one among all the projectivization. So extended isotopy is a diffeomorphism that extends isotopy of this, and we only look at the extended isotopy lives and so on. So the uh, anyway, so when you do this the extended isotopy, then this will also give you smooth extensions. So really the deformation space is just the quotient of these maps, which are extension of developing map by the extended isotopies of these forms, and then we give a CR topology. So the nice thing about this O-head is the quotient space is a compact manifold, so you don't really working with non-open open manifold. So and this and then there's this action and then finally you of course have to do PGL n plus one action by conjugation. Okay, so you get this map. Okay, so the thing that we need to do is to find the local homeomorphism theorem. So we have these type of n's here, and then suppose we have some open set here, then we can define this S1B to be for these Rn's to be the sending these holonomial homomorphism to the common fixed point of these representative n's, satisfying this equivariance property. And then you can do it for also the dual for the T type n's with satisfying these properties. And these are called the dual fixed sections. And then you combine these two into these two, and so on. So E tilde I for each Pn has a radial foliation, and this EI has a T foliation here. Uh, so also in the T case, you might even have a horospherical ends, and then these will be determined. So the tangent hyperplane will be determined by the I spector. Okay, so next we want to show that horospherical end can be perturbed. So we look at this representation space where these are also either lens or horospherical and that kind of space. So the point is, if you have some horospherical type end here, then if you perturb this holonomy, you can still obtain a lens type end. So if you are restricted to this space, or it will it will lie. So for the Tn horosphere case with the Tn, then you can also get the. So if you're lying here, then you can also get the lens-shaped Tn if you perturb it. So the basic proof is that so you want to parameterize this horosphere and in the equivariant manner. And as you change the holonomy, then you have these things deforming, but still you can show that they're continuously changing. So you can define that they can they they can deform well, and so so you can find the develop, and then of course for the Tn, you can also do the similar argument, but now you work with the total geodesic boundary, so on. Okay, right. So the perturbation is that you have this general lens type, then there's some sufficiently small neighborhood so that they will always. So if you perturb in here, then you always get the lens or the total geodesic lens type end. Okay. Okay, and then 9.43 is local homeomorphism theory. Um, so the thing is that so you have this n, and then these thing developed, and this is a local homeomorphism to open subset. So we only work with stable representations here, and then of course that's uh, and then for the unique, if you give a unique case, so this is when you have a fixing section defined on B, this B, then you can do this as a local homeomorphism onto B. So if this B is an open subset here, then and then of course B is of course conjugation invariant, so it will map to open set here. Okay, and then for the unique case, you still have a uh, local homeomorphism. So the basically this thing will follow from this, because this section is actually just by uniqueness, section is always defined. So that's why you can do this. And to prove this 9.45, you need to send this projective structure to H. Whole map is local homeomorphism. So we just want to work in this home space with this is the isotopy space before cautioning by the SLM plus 1R. And so the basically, so you have some point here, then you want to change the holonomy, then in V, then you can say that still you can realize by the projective orbifold. And so we just follow the Locke's argument that you can cover this all by some finite collection of compact neighborhoods inside some open neighborhoods, and so on. And so first of all, we give some ordering so that the end orbifold. So there's of course end orbifold here. So end orbifold, end neighborhood has higher than everything else, and then you look at the intersection. So you look at the intersection with the largest number with the highest indices in the dictionary order, and then you deform from there, okay, using this deformation theory about a sub-theory of some kind. And then so you first deform from the end, and then you look at the highest index ones, then meeting the end first, and then you keep going with this. Okay, so then everything will patch up. Okay, so these are the generalization of the Locke's argument in this case. Okay. So these things work with the Tn as well, and so on. Okay, and finally, I want to talk with the previously defined deformation space. So this, so we record for the Coxeter orbifold, which is not necessarily compact. So there, I only remove some vertices only here, and So we denote this to be the same set as this one, but we give a CR topology just by just restricting to O instead of this O bar, which I did a comp. So this should be tilde, sorry. I mean instead of O hat. So so then just doing that is actually equivalent to doing it like I did. So I just showed that they are actually homeomorphic. So the reason is, of course, if you map this to this side, and this is actually continuous because this has a fewer sort of base spaces. So it has a fewer bases, so you can also show that they are smooth. And but of course, the more difficult thing is to get the inverse map and right. Right. So you need to look at the jets and the topology given here, and so look at the bases. And the thing is that this has a more bases than this one. So therefore, this inverse image is going to be still a basis. So therefore, it's open. I mean, it's continuous. Yeah. So I showed this is continuous, and we want to find the inverse. So actually the problem is to find the inverse here. So continuously is clear, but you want to find the inverse. So to find the inverse, the thing is that you want to change the element in the second space so that it becomes an element here. Okay. And a way to do it is the radial. So you have to fix these pairs of n, and then you have to do these radial and projection projectivization here, and then you can show that there is actually an inverse map, and then finally I have to show that these are continuous. Okay, so the continuity again is to some argument with the basis and the kind of things here.